Hi, okay, so this is lesson 2 in deductive reasoning, and just a little review of inductive reasoning from the previous lesson. Sorry, this is deductive reasoning, but just a little review on inductive reasoning. So recall that inductive reasoning is a type of reasoning in which we arrive at a conjecture or conclusion based on experience or observations of patterns. It's not a mathematical type of reasoning, it's just basically based on experience, what we can observe. Excuse me. Inductive reasoning, however, does not guarantee that a conjecture is true in all cases, no matter how many examples we have to support that conjecture. So just because we cannot find a counterexample does not mean that one does not exist. There may well be a counterexample that we cannot find that proves that the inductive reasoning or the conjecture does not prove to be true. Inductive reasoning can play a part in a discovery of mathematical truths, but some other form of reasoning is required to actually make the proof. So using logic to reason, and this is more like perhaps a mathematical way of looking at things. Here it's saying that Susie dropped off a film at Quick 1 Hour Photo. Quick 1 Hour Photo, it advertises that your film will be developed within 1 hour or there's no charge. Susie dropped off the film at 10 o'clock and it wasn't developed until 11:15. What can Susie deduce from this information? Well, Susie's film will be developed free of charge, basically. So, deductive reasoning, also called logical reasoning, is the logical process of using true statements to arrive at a conclusion. So this is what's happening about Susie's film. They've told her it's going to be developed free if it's not developed within an hour. It wasn't developed within an hour, therefore you can say that it won't be developed free of charge. So in the scenario above, Susie used deductive reasoning to conclude her film would be developed free of charge. So here is example number 1, and if I can just pull this up now, get my pen working, let's see if this works. It's a little bit thick. Oops, move it over, and let's see. Okay, having trouble with that. So, write a conclusion which can be deduced from each pair of statements. Every whole number is an integer. That's true. 6 is a whole number. That's also true. So therefore we can deduce that 6 is an integer because it is a whole number. Every whole number is an integer. 6 is a whole number, so 6 must be an integer. B. Water freezes below 0 degrees C. The temperature is negative 15 degrees C. So what can we deduce? Well, water should be frozen. Definition of a theorem. A theorem is a statement which can be proved using logical or deductive reasoning. Statement which can be proved using logical or deductive reasoning. So let's look at class example number 2 here. In class example 2, here we go. In lesson 1, class example 4, we used inductive reasoning to write a conjecture that the sum of 3 consecutive integers was divisible by 3. Use deductive reasoning to prove the following conjecture. The sum of any 3 consecutive integers is a multiple of 3. So we're going to use deductive reasoning this time. So how do we do that? Excuse me. Well, different ways to set this up, but you could say that the first integer is n plus 1, and then the third one is n plus 2. And the way it's written here is that the first number happens to be n minus 1, the middle number is n, therefore the next one up must be n plus 1. So these are three consecutive numbers, one after the other. N has a certain value. It's the value of the middle number. This is the one below, this is the one above. Now, we have to deduce the following. The sum of any three consecutive numbers. So this is any three consecutive numbers. We don't know what n is necessarily right here, but these definitely are three consecutive integers. And we've got to deduce that these are a multiple of 3. So if we add n minus 1 plus n plus n plus 1, we should be able to deduce that it's a multiple of 3. So let's add all this up. We can see that that's n plus n plus n is 3n. And here we have a negative 1, and here we have a plus 1. So in fact, it equals 3n. And so we can see this must be a multiple of 3. So 3n is 3 times any integer, whatever n number we happen to pick. It doesn't really matter, because we can see that it's going to end up, the sum of these three consecutive numbers will be 3 times n. So it is a multiple of 3. Moving on to class example 3. Complete the chart and make a conjecture using inductive reasoning. So the chart here is filled in already, but if we were to look at the results here, we have to make a conjecture using inductive reasoning. So first of all, choose a number less than 10. So case 1, we can choose 1. In the second case, second trial, we can use 2, and third, we can use 3. Now let's see what they're telling us to do here. They say to add 7 to the number. Well, that takes us to 8. If we multiply that now by 2, it takes us to 16. Subtract the original number, which was 1, so that gives us 15. Subtract 2, brings us to 13. Subtract the original number again, brings us back to 12. Well, we could do the same for any set of numbers that we choose between 1 and 10. We could try 5 or 7 or even 9 or whatever. Now it looks like it always ends up at 12. So our conjecture, make a conjecture based on what we've observed here, I guess, due to inductive reasoning, we can say, well, no matter what number is chosen, the final answer has got to be 12. That's based on observation or experiment. Okay, so let's look at part B. Prove this. Prove your conjecture using deductive reasoning. Okay, so we're going to use deductive reasoning this time. So how do we do that? Well, we can take a number and let's just represent it with a letter x, because we're not going to take a specific case, because we have to prove it basically for all numbers. So in this case we use x. X just represents any number. And we'll go through the same steps here. We'll add 7. We'll multiply that by 2, so we'll get this. So we'll work out the brackets. 2 times x is 2x. 2 times 7 is 14. And then it says subtract the original number. So we're going to take x away from this. So one of these x's will depart. Or we can just take this and minus the x. So we're left with just x plus 14. Subtract 2. So we're going to subtract 2. That'll bring us down to x plus 12. And then subtract the original number. So we're going to subtract x again. So yes, it looks like we always do end up with 12. Well, why is that when you think about it? Well, you're adding 7 here. And what else are you doing? You're multiplying by 2. You're subtracting the original number. You subtract 2. And then subtract the original number. So you can do this for any number x, and you always end up with 12. So in a sense, using this deductive reasoning, using x as any number, we've proved that whatever the original number is, it's always going to end up, the series of operations is going to end up giving us 12. Does the original number have to be less than 10? Good question. Well, it seems that using this deductive reasoning, it doesn't matter what x is, it could be 105 for that matter, we'll always end up with 12. So no, it doesn't matter what number it is. So in this lesson we'll be considering statements involving odd numbers or even numbers. Okay, so odd numbers or even numbers. So what does that mean? If we're going to use a notation for any odd or even number, what kind of notation are we going to use? So if we want an even number, we can take any number n, even or odd. If we multiply it by 2, if it's an odd number, multiplying by 2 will turn it into an even number. And if it's an even number multiplied by 2, it still remains even. So 2 times n is going to give us an even number no matter what. Now how do we get an odd number? Well, we can subtract 1 from 2n. So no matter what number we've chosen for n, multiplying by 2 makes it even, but subtracting 1 will make it odd. It doesn't have to be 2n plus 1, it could also be 2n, sorry, it doesn't have to be 2n minus 1, it could be 2n plus 1. Okay, so these are notations for even or an odd number. That ensures it's even, this ensures it's odd. Alright, let's look at example here, number 4. Explain why 2n, when n is a member of natural numbers, so remember natural number starts at 1 and goes up in single units, so it could be any number starting at 1, 2, 3, 4, so any whole number starting at 1 and up. Does not include 0, however. Okay, 2 times n can be used to denote every number, every even number. Explain why. Well, as I said above, 2n represents any multiple of 2, and all even numbers are divisible by 2. How about 2n minus 1? Explain why that can be used to denote every odd number. Well, again, every odd number is 1 less than an even number. Or it could be plus, it could be 1 more than an even number. Okay, consider the following statement. Example number 5. When 2 odd numbers are added, their sums are always even. Well, we know that to be true in life, right? 3 plus 5 is 8. 11 plus 13 is, what, 24? And if we go on, we can see that this is true. So using inductive reasoning, in other words, using examples, 1 plus 5 is 6, 3 plus 11 is 14, 5 plus 7 is 11. These are all even if we add 2 odd numbers. But now, part B, use deductive reasoning, some mathematical proof, to prove the statement above is true. Well, let's use our terms for odd numbers. So 2n minus 1 is an odd number, whatever n happens to be. And we can use another odd number, a different odd number. Let's use 2 times m this time. M is just a different number. This will also be odd, but it'll be a different odd number. Okay, so let's add these 2 odd numbers. 2n minus 1 plus 2m minus 1. That gives us 2n plus 2m, and then negative 1 gives us negative 2. Now, let's factor the 2 common, which is common to all 3 terms. Let's factor that out. We do that, we get in the brackets n plus m minus 1. But this whole bracket is multiplied by 2. So no matter what this number is, even or odd, it's multiplied by 2, so it ends up being an even number. This is a multiple of 2, and therefore it's even. So we can see that by adding 2 odd numbers in this way, we've used deductive reasoning to prove that we get an even number. Whatever it is, it's a multiple of 2. Okay, so that's lesson 2. So basically complete questions 1 to 4. And we can move on also to lesson 3. So I'll just pause here and save this video.